Good evening all. Today I would like to discuss about rectifier. Okay, see here rectifier is a device which converts AC voltage into pulsating DC. Okay, now see here you can observe the block diagram of this figure. See here I am giving AC input voltage to the rectifier. Okay, then already we know that what is the purpose of rectifier. It converts AC voltage into pulsating DC. Okay, pulsating DC is nothing but the output of DC voltage containing some amount of ripple content. That is nothing but DC output voltage is also having AC, some AC quantity is present. Okay, by using filter equipment we can remove this AC ripples. Okay, after this filter we will get pulsating DC only. Okay, by using regulator device we will get pure DC. Okay, this is the process of getting input AC voltage into output pure DC. Okay, to get pure DC we require a rectifier as well as filter as well as a regulator, but in this topic we are only dealing about rectifiers. Okay, now here based upon the applications, rectifiers are classified into two types. One is half wave rectifier, second one will be full wave rectifier. Again full wave rectifiers are classified into two types. First one is center tapped rectifier, second one will be bridge rectifier. Okay, now we will discuss about half wave rectifier. Okay, see here it is the arrangement of half wave rectifier. Okay, this half wave rectifier consisting of step down transformer and a diode, PN junction diode, and a load resistance RL. Okay, see here the secondary side of the transformer is having a PN junction diode is connected in series with the load. Okay, the output voltage is measured across the load. Okay, this is the construction of a half wave rectifier. Okay, now we will discuss about the operation of a half wave rectifier. Okay, now see here when AC supply is given to the transformer, right, then here we are having AC supply. The secondary of transformer is having AC supply, right? Okay, now see here this is the AC voltage waveform. AC voltage waveform is having positive half cycle and negative half cycle. Okay, that means based upon this positive half cycle and negative half cycle, I am dividing the total operation into two stages. That is, first stage is operation 1, second stage is operation 2. Okay, now see here during positive half cycle. Okay, during positive half cycle the polarities across the secondary transformer will be plus comes here and minus comes here. Okay, during positive half cycle plus comes here and minus comes here. Now see here plus is given to anode and minus is given to cathode, right? Then diode is in forward bias. Okay, when diode is in forward bias it acts as a closed switch. Then if we apply KVL here, the output voltage will be same as input voltage. Output voltage is same as input voltage. That means during positive half cycle, okay, the polarities of secondary transformer will be here plus and here minus. Okay, then the diode is in forward bias. When diode is in forward bias, it acts as a closed switch. Okay, then the output voltage will be same as input voltage. Okay, now see here during positive half cycle the output voltage will be same as input voltage. You will get the waveform like this, output voltage. Okay, that is about operation 1. Okay, next operation 2, that is during negative half cycle. Okay, during negative half cycle the polarity across the secondary of transformer will be here minus, here plus, right? Minus is given to anode. Now observe here minus is given to anode and plus is given to cathode, right? Diode is in reverse bias. Okay, here diode is in reverse bias. When diode is in reverse bias it acts as a open switch. That means no current is flowing through the diode, then there is no current flowing through the load resistance. Then V0 is nothing but I0 into RL. Output voltage is also 0. That means during negative half cycle the diode is in reverse bias and it acts as a open switch. No current is flowing through the load resistance. Then output voltage will be 0. That will be observed here. The output voltage will be 0. Again this will be repeated, right? Again positive half cycle Diode is in forward bias. It acts as a closed switch. Output voltage will be same as input voltage. Again negative half cycle, output voltage will be 0. Next see here, this is the I0 is the output current. Already we know that output current is nothing but I0 is equals to V0 by R. Okay, because of this presence of resistance here, because of this resistance value, this value, because of this presence of resistance, what about the current I0 will be less. For example, assume output voltage will be 230 volts, okay, and resistance will be 10 ohm. Then I0 will be 230 by 10, you will get 23 amperes, right? That means the magnitude of current will be less, right? That will be represented waveformatically. This is the I0 value. See here, the magnitude of I0 is less when compared to V0 magnitude. Okay, but voltage and current both are in phase in case of resistor. Okay, now those are the waveforms of a half wave rectifier. Now see here, from these waveforms the final conclusion is, in case of half wave rectifier, we will get output voltage or output current only in one half cycle. Hence the name of this rectifier is half wave rectifier. Okay, just see here, in case of half wave rectifier, the output voltage present only in one half cycle, hence it is known as half wave rectifier. Okay, next we will see the specifications. That means there are some specifications, that is average value, RMS value, form factor and peak factor, peak inverse voltage, efficiency, ripple factor and transformer utilization factor we can calculate for each and every rectifier. First we will discuss about average value. Okay, average value or DC value or mean value, all are equal. Average value or DC value or mean value. Okay, here I am considering voltage V average, or that is equals to VDC is equals to 1 by T integration 0 to T f of omega t into d omega t. Okay, here the function f of omega t will be sinusoidal voltage, that is Vm sin omega t. If I substitute here, V average is equals to, see here from the waveform, from this output, every 2 pi seconds waveform is repeated, right? Then time period will be 2 pi 1 by 2 pi integration 0 to 2 pi actually, right? But here the output voltage and the output current is present only from 0 to pi. From pi to 2 pi will be 0, right? That can be written here by using integral by parts. Okay, 0 to pi Vm sin omega t into d omega t. From pi to 2 pi voltage value will be 0, right? That is pi to 2 pi 0 into d omega t, you will get 0. Then V average is equals to 1 by 2 pi integration 0 to pi Vm sin omega t into d omega t. That is V average is equals to Vm by 2 pi integration of sin omega t, you will get minus cos omega t. Upper limit will be pi and lower limit will be 0. If I substitute those values here, V average is equals to Vm by pi, okay, into 2 and 2 will be cancelled, you will get average value in case of half wave rectifier will be Vm by pi. Okay, similarly RMS value, okay, Vrms is equals to root mean square of 1 by t integration 0 to t V square omega t into d omega t, that is 1 by 2 pi integration 0 to 2 pi Vm sin omega t whole square d omega t. But already we know that the sinusoid output voltage will be present only for 0 to pi. From pi to 2 pi will be 0, right? That is 1 by 2 pi integration 0 to pi Vm sin omega t whole square into d omega t plus pi to 2 pi 0 square into d omega t, right? That is Vrms is equals to under root Vm square by 2 pi integration 0 to pi sin square omega t d omega t. Okay, we don't have a formula for integration sin square omega t, right? Hence I can written as 1 minus cos 2 omega t by 2. That is Vrms value is equals to under root Vm square by 2 pi integration 0 to pi 1 minus cos 2 omega t by 2 into d omega t. Okay, next, then Vrms value is equals to under root Vm square by 4 pi. Okay, here I can take 2 as 2 is taken as outside, you will get Vm square by 4 pi. Integration of 1, you will get omega t. Integration of cos 2 omega t, you will get sin 2 omega t by 2. Substitute upper limit as pi, lower limit as 0. You will get Vrms value is equals to under root Vm square by 4 pi, pi minus, right, pi minus sin 2 pi value will be 0, upper limit is over, minus lower limit 0, minus of minus plus, again sin 2 into 0 sin 0, again you will get 0. After simplification you will get Vrms value is equals to Vm by 2. Next, form factor. Form factor, it is defined as the ratio of RMS value to the average value, right? Form factor is equals to RMS value divided by average value. Okay, that is Vm by 2 divided by Vm by pi. You will get pi by 2, that is equals to 1.57. okay. Next, peak factor. It is defined as the ratio of maximum value to the RMS value. Okay, peak factor is equals to maximum value is nothing but Vm. In case of voltage, RMS value is equals to Vm by 2. You will get 2. Next, peak inverse voltage. Okay, the amount of reverse voltage that can be bared by the diode is nothing but peak inverse voltage. Okay, now see here from the operation. Okay, when diode is in reverse bias, right, it acts as a open switch, right? No current is flowing through the load resistance. In this condition, total supply voltage is applied across the open circuited contacts of the diode. That means the diode must and should bear this voltage. Okay, in case of AC supply, the maximum amount of voltage will be Vm, right? That means this diode must and should bear this voltage. That is nothing but peak inverse voltage. Peak inverse voltage is nothing but the amount of reverse voltage that can be bared by the diode under reverse bias condition. That is nothing but PIV, that is equals to minus Vm. Okay, next, ripple factor. Ripple factor is nothing but the amount of AC component present in the DC output voltage is known as ripple factor. Okay, ripple factor gamma is equals to, we can written as VAC by VDC. Okay, here VAC is equals to under root Vrms square plus VDC square, that is Vrms is equals to under root VAC square minus VDC square. See here approximately VAC and Vrms values both are equal only. Okay, don't confuse here. Okay, for that purpose here gamma directly here I am writing Vrms by VDC. That Vrms is equals to again under root VAC square minus VDC square. Okay, then ripple factor gamma is equals to under root VAC square minus VDC square by VDC. I can take this VDC in root, then you will get VAC square minus VDC square by VDC square. If I simplify that equation, VAC by VDC whole square minus 1, right? Here already I told you VAC is approximately equals to RMS. VAC is in place of VAC directly I am substituting Vrms. Then gamma is equals to under root Vrms by VDC whole square minus 1. Okay, already we know that in case of half wave rectifier, Vrms is equals to Vm by 2 and VDC is equals to, VDC is nothing but average value, that is equals to Vm by pi minus 1. If I substitute all those values, you will get ripple factor zeta equals to 1.21. Okay, next, efficiency. Okay, efficiency, it is defined as the ratio of DC output power to the AC input power. Okay, that is efficiency neta is equals to PDC by PAC into 100. Okay, here we are measuring output power, DC power across the load, right? That means current flowing through that load is nothing but only DC, right? Output of the rectifier is DC, that is nothing but IDC square into RL. IDC square into RL. Wait a minute, see here. Here output power across this IDC, right? IDC square into RL, that is output power. Similarly, next input power, we are measuring input here, right? Okay, output is DC. Input is AC, right? AC is nothing but AC meters always reads RMS value, that is IRMS square into RL. But if we consider diode under forward bias condition offer some forward resistance, that will be represented by R suffix F. Okay, that means AC power PAC is equals to IRMS square into load resistance RL plus under forward bias condition diode forward resistance is RF. Okay, where RF is diode forward resistance. Okay, then percentage efficiency is equals to PDC by PAC into 100. PDC is nothing but IDC square into RL divided by PAC is here IRMS square into RF plus RL. Already we know that IDC is equals to IM by pi whole square into RL. IRMS is nothing but IM by 2 whole square into RF plus RL. Okay, here IM square and IM square will be cancelled, right? Then you will get 1 by 2 whole square 4 comes to numerator, 4 by pi square into in numerator we are having RL divided by denominator I can take RL as common, right? Then I will get 1 plus RF by RL and RL will be cancelled. RF by RL value will be very less, hence I can neglect that value. Then percentage efficiency will be 40.6%. Okay, next last term will be transformer utilization factor. Okay, transformer utilization factor, it is defined as the ratio of DC output power to the input VA rating. Okay, that is different, input VA rating of the transformer. Okay, now see here, transformer utilization factor is equals to PDC by PAC, volt ampere rated values. Okay, DC power is nothing but VDC into IDC, that can be written as VM by pi into IM by pi. Okay, whereas AC power VA, volt ampere rated, is nothing but VRMS into IRMS. See here, source is a sinusoidal voltage, that means source voltage is a sinusoidal voltage. For a sinusoidal voltage, VRMS value will be VM by root 2. But the RMS current is flowing through the diode, right? Okay, that means in case of half wave rectifier, the RMS current will be IRMS equals to IM by 2. This is the change. You need to identify this change. Okay, then transformer utilization factor. Here I am considering 1 by TUF. That is nothing but PAC by PDC, right? Okay, PAC is nothing but VRMS into IRMS, right? VM by root 2 into IM by 2 divided by PDC, VRMS into IRMS, that is VM by pi into PDC, right? VDC into IDC, that is VM by pi into IM by pi. If I simplify this equation, I will get pi square by 2 root 2. Then transformer utilization factor will be 2 root 2 by pi square, that is equals to 0.286. That means in this rectifier we are utilizing 28.6% of transformer. Okay, that is nothing but a transformer utilization factor. Here the advantages will be low cost, simple in design. Okay, see here, design will be simple, we are using only one diode and one transformer, cost is also less, right? Next, the drawback of the half wave rectifier will be ripple factor is high. Okay, always ripple factor should be less, but here ripple factor will be, we are getting 1.21, right? That means 121% of AC component present in the DC output voltage. That is one drawback. Next, efficiency is low, only we are getting 40% efficiency, right? Efficiency indicates the performance of a device. Okay, when efficiency is less, performance will be poor, that means it will be damaged very quickly. Okay, that is also another drawback. And also transformer utilization factor is also less. Okay, to avoid those drawbacks, we introduced full wave rectifier. Okay, that is about half wave rectifier. I hope all of you understood this concept. Okay, thank you.